Today I want to talk about water and the law that surrounds drinking water, to talk about its quality, talk about what your rights are to clean water, to also give you a sense of what key threats are to drinking water, what your exposure might be, and what we might do about it, both legally but also personally. Water is a critical component of our environment in our bodies. Your body is close to 70% water. You can go for several weeks, 2 to 3 on average, without food. You can only go for about 4 minutes without air. And you can go for maybe 4 or 5 days without water before you die. So water is absolutely critical, and one of the key arguments I want to make today is that it's a largely neglected area of environmental law, given the rapid increase in our knowledge about chemical threats to water quality and where those threats come from. So what are the major challenges in water on a global scale? Clearly one is waterborne diseases. Diarrheal diseases are recognized to kill between 4 and 5 million people per year in Africa. Aquifers that cross property and jurisdictional boundaries are a critical issue. So many rivers form the boundary between nations or between states. The Connecticut River is a very good example, separating Vermont from New Hampshire. Point source control versus surface runoff. We've had a long history in the last half of the 20th century of trying to control point sources or pipe releases to water supplies, as opposed to thinking about how chemicals may accumulate on the surface and then be washed into rivers that are used for drinking water sources following serious rain events. Groundwater depletion, the Oglala Aquifer in the southwestern part of the United States and in the western part of Texas is being rapidly depleted, and its contamination is well recognized. Aquifers around the nation in most industrialized countries are now more intensively tested than they have been before, and it's recognized that they contain chemicals that never were anticipated to persist or to migrate. Private wells. The Safe Drinking Water Act has been established in the United States to require testing and control the chemical content only in water systems that supply more than 15 households, 15 or more households. So if you grew up perhaps in a rural part of the nation, or you live outside of New Haven, you may have your own well, as I do. So I have a 600-foot deep well, and when I purchased my house, I was quite happy with that prospect, thinking that water on the surface would need to be filtered down through the soil before it got down into to the well. And it was quite striking. I had quite a lesson from a well driller. My well went dry one day. I didn't know what happened, so I called the well driller, and he came out, and it was a pretty remarkable lesson for me. Within 45 minutes, he had pulled up the wellhead, he'd coiled the water, coiled the pipe, and I recognized that I hadn't paid any attention to the fact that the casing that surrounds the well could convey water that had been contaminated on the surface down the side of the casing and into the underlying water supply. I'll tell you more about the plastics side of that story in a few weeks. So wells that service greater than 15 households are regulated under the Safe Drinking Water Act, which means that if a chemical is listed on the EPA's list, then community supplies have to test for the presence of that chemical. And if a maximum contaminant level has been set, that means that the provider has to demonstrate that that ceiling has not been breached, or he or she would have to install some sort of filtration system. So within Connecticut, by the way, that means that approximately 30 to 40% of the Connecticut population is getting water that is not managed in any way by the Safe Drinking Water Act. Surface water in the United States is generally believed now to be undrinkable for a variety of reasons, mostly because of biological contamination, the threat of E. coli, but also Giardia, which is carried by both humans and by animals in their wastes. Monitoring and surveillance needs much improvement. I'll talk more about the monitoring system that is currently in place and why it's deficient. Public water infrastructure also is inadequate. How many of you know the way that water moves from its source to your tap? What kind of equipment does it go through? What kind of filtration does it go through? What kind of land uses are allowed in the watershed that surrounds the lakes that provide New Haven's water supply? And what about the pipes that convey the water to wherever your tap is? Do you know what they're made out of? Are they plastic? Are they copper? Are they bronze? Are they metal? Are they leaded? There are many connectors in many cities that are quite old that are no longer allowed to be installed that connect the water main itself into your apartment or into your house, but they exist and remain because it's extremely expensive to dig up every connector and replace it with one that does not contain lead. How about your faucet itself? What's your faucet made out of? Well, many faucets are made out of brass, and increasingly they're made out of plastic that is painted to look like it's metal, painted silver. You have to be really careful when you buy a faucet system or you put in a drinking water supply system to really think deeply about the source of the materials and their leachability into your supply. The leachability is driven by a variety of factors. It could be heat. So, for example, you certainly would not want to make a cup of tea by turning your hot water tap on and then putting a tea bag in the water. Or you wouldn't want to feed infant formula to a small child by putting powder, for example, in a glass and then filling it up with hot tap water. Because the hot tap water is likely to leach more compounds from the pipe or whatever the conveyance system is than cold water would. How long do you wait before you to let the water run before you take a drink out of your tap? It makes sense not to drink a water that has been sitting in your tap overnight. You come back from vacation for a couple of weeks. We now recognize that water that sits in pipes takes up contaminants from the conveyance system. So all of these issues are worth thinking about in terms of infrastructure. How about water rights? Really, what are your rights to clean water? And the core question of this lecture is really how safe is safe enough? And how do we define safe, particularly using the language of the Safe Drinking Water Act? And finally, how does land use affect water supply? So many people are not at all thoughtful about where watershed boundaries in the vicinity of where they live. They're not thoughtful about how chemicals can migrate long distances. I worked in California in the Central Valley near Fresno for a while on a project where chemicals were recognized to migrate more than 5 miles from their point of application to an agricultural field into underlying aquifers. So it depends very much on the underlying surficial geology, the soil structure, the bedrock, the groundwater regime, how fast a chemical will move. Some move really quite quickly, others move really quite slowly if they can bind to organic matter. So once again, the Safe Drinking Water Act covers supplies that have more than 14 connections or more than 24 individuals. There are 53,000 water systems in the United States, and 43,000 of those rely on groundwater and about 10,000 rely on surface water. And they're roughly split 50-50, public and private. And there are 15 million wells in the United States that serve individual residences, and roughly 45 million people, maybe 15% of the population in the nation, are drinking water that is completely unregulated by the Safe Drinking Water Act. I wondered about this, and I wondered about what we could find out about well water vulnerability. And also, if a casing surrounding a well is cracked, that means that chemicals applied to the surface have a higher chance of migrating down the inside of the casing. So I asked the Department of Environmental Protection and the Department of Health here in Connecticut if I could get a hold of their database, GIS, a Geographic Information System that they had that identified the location of all wells in Connecticut. All wells that had been mapped and geocoded. And then I overlaid that data with surficial geology. And then I started looking at old air photos, wondering about former land uses. And a pattern started to emerge that in many areas that had been former agricultural lands, these had been developed into residential areas, and wells had been dug into those areas and provided unregulated water supplies. to almost 1 million people in the state of Connecticut. It's kind of an interesting story. When I asked for that database, I was denied access to it. This was post 9/11 because they were worried about releasing the geocoded data on precisely where the wells were. So I had to sign a paper that promised that I would be legally responsible for securing that data and maintaining its confidentiality, and I would not release it to anybody who could do something nasty to a public water supply. So what about compliance? How are we doing in the area of compliance? Well, 30 million people drink water each year. A little hiccup there for some reason. 30 million people drink water each year from systems that report violations of health-based standards. There are about 93 chemicals that are now on the safe drinking water list that have maximum contaminant levels assigned to them. So 30 million people, 10% of the population drinking water that that the systems have reported are in violation. 10,000 systems violated health-based drinking water standards, and about 80% of the public water systems have reported no violations. And EPA has issued 86,000 violations of federal requirements to monitor or to report results. So the overwhelming number of violations are associated with the failure to monitor and the failure to report. So if you don't look, if you don't monitor, you can't find a problem. And if you find a problem and you're a municipal supplier, that's going to cost a lot of money. You're either going to try to pass that cost back on to consumers as increased prices for prices per gallon for their water, but certainly you're not going to want to, excuse me, one second. There's commonly a delay in reporting. So what is an MCLG, a maximum contaminant level goal? EPA established both the maximum contaminant level, which is a legally enforceable limit, but they also established a maximum contaminant level goal, which is a health-based ceiling. So you would hope that the legal limit would be the same as the health-based limit, but that's really not the case. So the Safe Drinking Water Act creates the contaminant level limit as the highest concentration of a contaminant that's allowed, and it also allows a cost-benefit analysis that's required under the Safe Drinking Water Act to consider what the cost would be of meeting that limit. If the cost is found to be excessively high, they'll set a goal that would be higher to protect human health and allow a contamination level to be higher than that. So here's a chart that gets us to really what our present level of regulation is. And you see that after the Safe Drinking Water Act was passed back in 1976, that no new standards were enacted. It's kind of interesting. So Congress basically gives EPA the mandate to regulate and monitor water supplies, but EPA doesn't really do very much about it. This period in the 1970s and early 1980s was a period that EPA was concentrating on source emissions from smokestacks, as well as auto emissions, and also a variety of pesticides, but really it was paying very little attention to drinking water. So it added 7 volatile organic compounds in 1987, about 11 years later. Copper and lead were not revised based upon new evidence of their toxicity from data that had been collected back in the 1970s until 1991. So remember, I argued earlier that there's often this delay between recognizing that a compound is more hazardous than earlier thought before the agency would take action and set a new limit. We're seeing the same thing play out here. Well, Congress was upset at this delay, and they demanded that a variety of new chemicals be added, including 39 pesticides, volatile organic compounds, metals. So these were added in 1991. And then during the period of the 1990s, 7 years, there were no new standards. Now, it's kind of interesting because you might assume quickly that in a more liberal administration that you'd have more rapid listing of chemicals, you'd have a more protective character. This is not the case. so that the liberalism or the conservatism of the administration seemed to have little influence on this rate of adoption. So today we're sitting here with about 93 different chemicals, and just to give you a sense of how limited coverage and limited the protection level is, think about this, that among the 39 pesticides that are monitored and have these maximum contaminant limits, there are approximately 1,000 more that are completely neglected. Nobody's testing for them, but they're allowed to be used on agricultural crops, and many of these have not been fully studied to know how they move through different kinds of ecosystems or different kinds of geologic systems, and what their potential is to contaminate the water supply. Think also that more than 800 other chemicals, including industrial chemicals, have been detected in water supplies by the U.S. Geological Service. And by the way, the U.S. Geological Service is playing a really unusual role in this regulatory process, in that they sit within the Department of the Interior. They're completely unrelated to the Environmental Protection Agency, but they're playing a more vigilant role in monitoring chemical content and hazards in underlying aquifers as well as surface waters than the Environmental Protection Agency had during this period of time. So this is a history of neglect, of limited surveillance, and it's being driven by one fundamental characteristic of the statute. This is a listing statute, which means that every time a new chemical is discovered and EPA decides they hope to either set a goal or to set a limit, they're going to get a fight from all the municipal suppliers or the private suppliers, because the testing costs are going to be passed on to them. And these testing costs are often not minor. By the way, it's interesting to think about what the effect might be of establishing a new chemical limit. Well, it may mean that you need to conduct a brand new type of test. It may also mean that you need to install filtration equipment, perhaps activated carbon filtration, which is extraordinarily expensive. And the smaller the water system is, the more expense it's going to allocate per individual household. So if New York City, for example, is facing a new standard that EPA has adopted, they can pass the cost of monitoring and filtration on to a very broad group of people. But if you have a much smaller community, say in the rural West, of a couple hundred people in an isolated area, that's going to be much more difficult for them to comply. So there's been a trend towards source protection instead of consumer protection. And in part you can see this happening, what the public response to this has been, which is to rely increasingly on bottled water. And many people have the perception that bottled water is much safer than tap water is. Well, it's not at all clear that that is the case. Many people do not understand the filtration techniques of bottled water companies. We don't really have clear standards. And also, many of the companies that are marketing heavily in the United States are now foreign companies. So the public's perception of safety is really poorly founded in scientific evidence. Also, there's a story about plastic. What about the potential plastic ingredients to migrate into water supplies? I'll give you one example. About 15 years ago, I had bottled water in my house as we were putting in a new water supply system, and so the bottled water came in a jug that was polycarbonate, a 5-gallon jug. You probably have all seen these that you'd flip upside down. And I had left that bottle outdoors. Actually, I'd been away for the weekend. It was delivered on a Friday during the summer months, and the temperature had gone up to about 102. And it was sitting on my driveway in the sun when the ambient temperature was 102, so it was really baking. So when I opened the bottle and I put it on the stand, I found that it had a really very acrid taste to it, a bitter, acrid taste. So I called the water company and I asked the bottling company, what might that be? And the response was, oh, we'll have a new shipment out to you right away. It was probably just the cleaning agent or the disinfecting agent that we put the bottles through. Well, I studied the problem more intensely and found that they were using a disinfectant that was actually a registered pesticide. And also, this was perfectly allowable because it makes sense to try to disinfect water bottles that are coming back that may have had stagnant water within them. But somehow the rinsing process hadn't effectively removed the cleaning agent. Well, the bottled water problem goes on in that I look more carefully at the potential of plastics to migrate from the polycarbonate into water, and heat, solvents, such as some biocides are mixed with. Also, cracks in the bottles themselves can cause the chemicals to migrate more frequently. The offending chemical in this case is bisphenol A, and we'll talk more about that later. If you look across the maximum contaminant limits and you compare them to the public health goal, this study by the state of California found that the maximum contaminant limit, the allowable concentration, was often 2, 4, even 16 times higher than the health goal, which tells us that in many cases the agency is making a determination that we can be exposed at a limit that they believe is not health protective. There are other studies that have demonstrated a similar finding for other chemicals besides the elements. So one of the ways to think about the effectiveness of any statute is to think carefully about how it's monitored. So what sampling design should be created in order to figure out whether or not we're effectively searching for chemicals that pose the greatest threat? Well, I asked this question of the New Haven Water Authority and found to my surprise that systems of 25 to 1,000 people are only required to provide one sample per month. And it's pretty clear that there are certain climatological events like very serious rainstorms that can wash contaminants off of surfaces, whether it's an agricultural field or say a large shopping center parking lot, into surrounding water supplies if they are nearby. So thinking about the importance of the sampling period is really critical. And if recent reports have demonstrated compliance with certain standards, then EPA allows the testing to be limited to only 4 times per year. And for some types of systems, such as the New Haven Water Company, they've not found certain pesticides, so they're allowed to monitor only on an annual basis. They can appeal to the Environmental Protection Agency to reduce the periodicity of their sampling. And this, of course, is very important to them because it saves them a lot of money. Triazine herbicides provide a really good example of this in the Midwest. So triazine herbicides they're known as pre-emergent herbicides, and they're commonly sprayed on fields such as corn fields, and they're sprayed during the spring. And the spring in the Midwestern part of the United States is kind of famous for the intensity of its rainstorms. So the sampling design relative to the rain events really proved to be extremely important to the findings. You can pay more attention to this slide online, but these data demonstrate the ways that increasing the stringency of standards passes costs on to water supply companies and to people that are served in really an inequitable way that is dependent upon the size of the public water system. So I want to concentrate today and tell you a story about this chemical. This is a triazine herbicide, and it's now it's about a 27-year-old story, but atrazine has become infamous as one of the most heavily used herbicides in the world. Its uses in the United States include food crops, field corn, sweet corn, sugarcane, sorghum, winter wheat, guava, macadamia nuts. It's used also on non-food crops such as hay, pasture lands. It's also used in forestry. It's also used in residential and industrial and recreational areas, on residential turf, within parks and on institutional turf, also on golf courses, and it's used for landscape maintenance. And the whole idea behind an herbicide is to kill other species of plants so that they don't rob nutrients away from the desired or highly valued plant. So it's also sprayed on roadways. And this is an interesting idea. It'll be a great student project. Think about the number of miles of roadways in the United States that are treated with herbicides. You know, my town is a good example, a little town of Killingworth. They don't like to cut the vegetation next to the guardrails. So what do they do instead? They come along with a truck and they just spray the side of the road. Next time you get on Amtrak, take a look at the vegetation that goes along the track, and you'll see almost nothing. You'll see it devoid of vegetation. How do they do that? Is it just that they didn't plant anything? No, because seeds would blow into the area and they would grow and less chemicals were applied. So along major highways in the United States, along state highways, in many communities, in areas that have guardrails, along corridors that are used for power, power lines or rail, on the runways of many airports, pesticides are applied. So if you count up the total area in the nation where these herbicides are applied, you can quickly get up to hundreds of millions of acres of the landscape. It's really quite striking. So, you know, finding a chemical such as this in the water supply really should not be that much of a surprise. But no one has really looked systematically at where concentrations of applications are going on. But I'll give you one example of where you might conduct this kind of a study, and that's with golf courses. So that about $225 million per year in the United States are spent on chemical treatments of golf courses. There is almost no landscape that I could imagine, including agricultural lands, that are treated more intensely than golf courses, and particularly putting surfaces. So about $1,300 per acre of 35,000 acres of putting surfaces are receiving quite a variety of different biocidal compounds. As a nation, you know, we need to think about where are we applying chemicals the most, and we're doing it predominantly to field crops. Field corn, about 59 million acres of field corn is treated. Sorghum, sugarcane, sweet corn, and both processed and fresh form. So large percentages of these crops are treated with atrazine. So if you map out the concentration of atrazine in streams in the United States, you see it centered on the Midwestern part of the country, and this is the primary corn growing region. So what you find is concentrations in the microgram per liter level, which is a part per billion level, and the maximum concentration level, the MCL for atrazine, is I believe it's 3 or 0.3. And if you look in the nation, what you find, parts per billion, and if you look across the nation to the number of people now that the Environmental Protection Agency think are drinking residues of this chemical in the water supply, you see this adds up to millions of people. So large circles like the one around Texas, you know, represent more than 8 million people. Circles around Florida represent about 4 million people. So you see that they're finding it in the water where it's most heavily used for agricultural purposes. So this was first registered in 1958, and by registered I mean it was given a license. It's like a driver's license. So atrazine it's regulated under the Safe Drinking Water Act. It's regulated under the Clean Water Act as well. And EPA began a special review that they reserve for chemicals that they have particular concerns about in 1994. Now, special review has had a rather infamous history inside EPA, and I have a good friend who graduated from Yale who has worked her way up to a high level inside the agency, and she refers to EPA's parking lot. And the parking lot is a place where EPA stores chemicals, not literally, but figuratively, when it decides it's not going to take any regulatory action on them. So atrazine was put in the parking lot, so to speak, receiving little attention for much of the 1980s when these data came out, when people realized that the concentrations were going up. When the parking lot fills up with additional chemicals, it basically means that the chemicals take longer and longer to receive review, and you have a lower and lower probability that health-based standards are going to be set in response to new evidence of serious contamination or risk. Another problem with atrazine is that it's structurally so similar to other kinds of herbicides, including simazine and propazine, and it produces similar chlorinated metabolites. Metabolites are byproducts that the original compound breaks into, that it makes sense to think about how we might be exposed to clusters of these compounds instead of treating them individually. So remember my argument earlier that EPA's attention is focused chemical at a time. So they'll make a decision on atrazine without thinking about simazine or propazine. But in terms of your exposure, in terms of its behavior inside your body, there is a presumption that chemicals that are so similar in structure will behave similarly in your body and pose a similar threat. So as a society, we want the government to pay attention to these mixtures, particularly if there's a plausible reason that we might be exposed to the mixtures. So in 1991, the MCL was set at 3 parts per billion, and the MCLG was set at 3 parts per billion as well. And the compliance was determined based upon a running annual average, with quarterly samples required by EPA or a single average sample. Also in the late 1980s, this was classified as a possible human carcinogen. But then the Environmental Protection Agency reviewed it as not a likely human carcinogen. Now, how do they make these choices? Well, they submit evidence to what they call a scientific advisory panel. And I've had the experience of sitting on EPA scientific advisory panels for nearly a decade and reviewing new evidence of risk. And the decision on the part of the panel to recommend a classification as a carcinogen or not a carcinogen, or a chemical of high concern or low concern, it really depends very much upon who is asked to sit on the scientific advisory panel. And I want to recommend to you the work of a professor at Harvard, Sheila Jasanoff. Sheila came here as a visiting professor for a while, and her work has been very important on what she calls the fifth branch of government, which are these advisory panels. So evidence is often so complex that an agency is not really clear what they're going to do. Is the risk higher? Is it lower? Should we regulate? Should we just warn people? How are we going to manage this chemical? They'll submit this question to a scientific advisory panel to gain their advice. Well, the political makeup of these panels makes a terrific difference in guiding the ultimate outcome. So the Food and Drug Administration, the Occupational Safety and Health Administration, EPA, most regulatory agencies rely very heavily on these scientific advisory panels. But just because a scientific advisory panel makes a recommendation doesn't mean that you ought to believe it. Prior regulation, they looked at the chemical more intensely, and they found that prior regulation was insufficient, so that they deleted rangeland, millet, and pineapple uses. So instead of prohibiting the chemical outright, they would look at particular uses, probably uses that did not have a very high economic value, and decided to go after those, to prohibit or further restrict those. They also used what they called a restricted use classification. In pesticide law, FIFRA, the acronym Federal Insecticide, Fungicide, and Rodenticide Act, it has this restricted use classification. And this is an interesting idea. I was telling a section last night that it's similar to the idea of a pharmacist. In other words, in the world of pharmaceuticals, we have this intervening layer of expertise so that the pharmacist plays a role of interpreting exactly what the appropriate dose is for you, so that the physician doesn't give you the drug directly normally, although this happens in a hospital often. But in the pharmacy, you get access to a chemical that poses certain risks because experts are there behind the counter to make sure that you're getting the proper dose, and that you understand that there could be drug interactions, or that there may be certain side effects that you should be aware of. So this same concept was built into pesticide law, but in a very different way, of training licensed applicators. So if a chemical is classified as being restricted use because it is more toxic, or it's more persistent, or it poses a certain kind of a health threat, then someone has to be trained before they're allowed legally to apply it. And within the pesticide regulations, there is a provision so that, supposing I went and I got my license, So I was licensed to apply dangerous pesticides, particularly in, say, restricted areas that were ecologically vulnerable, or maybe inside schools or hospitals, so that I have the legal authority to delegate that responsibility to you. And if you have no training at all, it makes no difference. I mean, I would tell you what to do. I would tell you to follow the label directions very carefully. But remember what I was saying about literacy and background literacy. So how do you mix, say, a quarter ounce of a toxic substance in, say, water or in kerosene or some other solvent that it's supposed to be sprayed in? And how do you know that you've got exactly the right concentration? Well, it takes some mathematical skill to do that. And I've run across a couple of cases that I was describing last evening where people that were delegated this authority not only had a minimum level of literacy, but also had virtually no mathematical capacity to make these kinds of judgments. So EPA realized this eventually, and they started requiring containers that were, in a sense, foolproof, so that you would have you would tip it. They call it a tip and pour mechanism. So you could pour out only the correct proportion of the active ingredient, and then all you had to figure out was whether or not you had to add 1 or 2 gallons to. So this reduced the error rate. But if you are spraying a pesticide, as an example, and you've got a backpack on and you've got a spray wand, I mean, I could be spraying the edge of this podium and walking along. My cell phone could ring, I could stop, I could look at my watch, and then I could move on. And the effect would be what? Well, when I looked at my watch, wherever the wand was pointing, it would get a dose that probably would be dozens of times higher than if I were walking in a uniform way. There's kind of an interesting an analog to that with respect to spray planes or tractors. So you can imagine a tractor that has a bar across the back of it, across the back end with holes on it, such as it's going to irrigate a field. Well, the truck goes along, gets to the end of the field, it turns around, comes back this way, and eventually it covers the entire field. Well, if it has the same application rate, the same emission rate from the pipe, regardless of the speed of the truck, where in the field are you going to get the higher concentrations? At the ends of the field, where the truck slows to turn around. Similarly, if you can think about a spray plane coming in and spraying the hypothetical field, which is the platform up here, they pass this way, then they come back and they pass another way. I've seen farm workers in California standing there with just shorts and a straw hat on, kind of waving as a marker for the spray plane being sprayed repeatedly. There's an occupational side to pesticide control that I don't have time to express to you. But then you get this overlap of the spray in the field. So these kinds of practical conditions have a really important implication for how you set up your sampling design. So if you sampled in the middle of the field that was treated by the truck or the tractor, you're going to get a lower level of concentration than if you sampled at the end of the field. The same may be the case with respect to spray planes and the way that they spray fields. So the Dancer regulation is one where the government will say, look, we've got to cut back your use. We have to protect the water, or we want to reduce worker exposure. And the industry that manufactures it will say, well, you know what, don't cut back in this area. Cut back and restrict its use on a specific commodity, probably one that is not an economically productive one for them, or a particular kind of use. So the argument about what uses are restricted as opposed to which ones are prohibited gets quite technical quite quickly. So if a chemical comes back as a recognized serious threat to human health, that doesn't mean it's going to be prohibited. Prohibition is very unlikely. I mean, there have been so few bans in environmental history, probably fewer than 300 bans, outright bans of chemicals. I talked to you about a couple of them. DDT is a good example, and aldrin and chlordane, these are all pesticides. But for the vast majority of compounds, instead you get this minor revision in the way the chemical is allowed to be mixed or applied. It is put into the restricted use category. It's allowed to be used on corn but not on another crop, so that the market share can be maintained. Here's a graph of the seasonal pulse of atrazine in water supplies that was recognized in the Midwestern part of the United States. You can't see the years here, but this is 1995, 1996, 1997, 1998, and you see this pulse that, because they apply it in the spring, and then the rains will like wash it into the surrounding water supplies. Well, so another sampling design issue here that really is critical to the effectiveness of the statute is that if you decided that you were going to sample, say, in September of each year, you're going to miss this pulse. So it's only by sitting down and thinking about the method of application, the timing of the application, and thinking about it in a more systems or ecological manner that considers climate, that you would be able to pick this up. There is a very interesting legal debate as well about what this chemical is doing, where it's moving, and the U.S. Geological Service found that it travels actually hundreds of miles from its site of application. So it's running off the fields, it's getting into streams, and it's getting into rivers, such as the Mississippi River. It's moving long distances. So this study found that states, some states were receiving 50% of their pollution load from out of state. So if atrazine is reaching, say, Louisiana, but we know that it's not applied in Louisiana, what right do they have to sue the Environmental Protection Agency for the failure to regulate that chemical's application up in Ohio or Illinois or in Minnesota? And they do have the authority to sue the Environmental Protection Agency or particular chemical companies that are responsible. So this transboundary movement of these chemicals raises a very serious issue. And also you've got to think about the fact that many of these cities get their water supplies from these rivers. And they use filtration systems that do not have the capacity to extract many of the pesticides that are used. So water is typically filtered by running it through sand to take out particulate matter. Then it's treated with chlorine. It's not normally treated with activated carbon, which could bind to these chemicals. Now that should ring bells in your head if you're concerned about your own water intake, because water is the most consumed food in your diet. It should ring a bell that you should be concerned about the quality of water in your tap, and you should think carefully about the wisdom of using activated carbon at the tap, because it's not likely that the government has kept it perfectly safe. So I'm going to scoot ahead here with one final aspect of this story. The atmospheric transport of some of these chemicals was a surprise to many, inside the agency as well as the scientific community. I ran into this in California when I found that a chemical, dibromochloroPropane, that had been injected into the soil in cotton fields had actually volatilized and gotten up into the fog. Anybody here from the Central Valley? Well, the Central Valley of California, which is sandwiched between the coastal range and then the Sierras, is a flat basin. It's a former lake bed. And climatologically, it's interesting because a fog will settle on that area and stay there for a good part of January, sometimes December, 6 to 8 weeks. So what they found was DBCP was actually volatilizing, and it was detectable in the fog. They found toxaphene that had been applied in Texas in the Great Lakes. Then they found atrazine in the Great Lakes as well. So 0.6% of atrazine is deposited in one study in rainfall. And the concentration of atrazine in precipitation in some areas where it had not been applied was 1 part per billion. And what did I tell you the maximum contaminant level was? 3 parts per billion. It's fairly striking. So it's moving long distances in clouds and raining down, and perhaps acting as a pre-emergent herbicide to areas where it was never intended to be used. So the degradation of the chemical in aquatic environments is increasingly a concern. The half-life is between 41 and 237 days, an average half-life of the chemical of 159 days. And Lake Michigan is a repository for atrazine because of its use, particularly in Minnesota and Michigan, Indiana, Ohio, and the pattern of rainfall in that area. So it's cold water, it's low productivity, it's high pH, low nitrate, and low dissolved oxygen, all contribute to increase the persistence of the chemical. So the estimated half-life in Lake Michigan is about 31 years. So EPA conducted a study that found that when they tried to figure out what the mass balance was of atrazine, or is of atrazine. So atmospheric wet deposition is about 2,493 kilograms per year. The watershed loading directly in surface water runoff to the lake is about 5,000 kilograms per year. 2,500 kilograms exported to Lake Huron and exported to Chicago by water diversions, a more minor amount. And even the lake itself is volatilizing the chemical. So recognizing that the agricultural practice of using atrazine as an herbicide and EPA's neglect of this compound and misunderstanding of its ecological behavior could cause a gradual buildup to 182,000 kilograms of the compound sitting in the lake was really quite striking. So I'm going to just pause with reflections on the work of Tyrone Hayes, who is a former chemical company employee, a scientist who worked for Syngenta. And Tyrone Hayes has been responsible for some controversial work. So he took his students and he rented a tractor trailer and they drove across the country taking a look at the concentrations of atrazine in leopard frogs. And what was interesting about his finding, because he sampled from areas of the country where the leopard frogs lived, but atrazine was not used, and then he went into the heart of the Midwestern atrazine use belt and sampled in those areas, and he found obviously higher concentrations in the areas where it was used, but he also found that these frogs had both ovaries and testes. So his argument is that this chemical is hormonally active, at least in the African clod frog. And he also is claiming that there are important lessons here for humans, that this compound could be also hormonally active in humans. So atrazine, he argues, in exposed males that have ovaries in their testes also had much smaller larynxes. And larynxes are important if you're a frog because it's a way that you can understand where other frogs are, or other frogs can understand where you are for reproductive success. And it's also recognized to lower the testosterone levels in frogs. So I'm not going to go further today other than to suggest that there's a whole emerging area of concern now about hormonally active compounds, and atrazine is a good compound to pay attention to. Okay, that's it for today. Thank you very much.